Thank you for coming here, and let's get started with what this series will be about. Before we actually outline the plan, we need to go through the preliminaries. First of all, this playlist isn't really intended for the bare beginner, so I'm not going to be explaining what the counterfactual regret algorithm actually is. If you don't know what it is, check out some of my older videos from 2.5 years ago. 2.5 years ago, we did implement the algorithm in F#, so you can go over here and take a look at this, implementing the counterfactual regret algorithm, integrating the counterfactual regret algorithm with the Leduc game. I'm playing a game versus the bot, implementing Monte Carlo counterfactual regret. Let's see, I'm going to leave a link in the description, but you can also go to my channel and just take a look at the playlists. And let's see, here's the, yeah, take a look at the full playlist here. And the video is somewhere in the middle. We also worked on this algorithm in the spiral playlist. And the spiral playlist is more advanced material than the, how do I put it, than the F# one. And actually, in the first half of this playlist, we tried programming FPGAs in Spiral, and that didn't really work out, and I kind of forgot about it. Then we started working on GPU programming, matrix multiplication. Over here, we started working on the rock, paper, scissors game on the GPU. We first implemented it on the host in Python. Let's see, serialization, heads up no limit on the GPU. Where did we implement counterfactual regret? Sorry about this. Random neural agent on Leduc, random neural agent on Hold'em. Parallel tabular CFR implementation. Really? Am I not supposed to have implemented it somewhere? So sorry about that. Integrate. Yeah, I think we actually implemented a parallel tabular implementation of CPR on the GPU directly, but yeah, if you're a beginner, that's definitely not the place where you want to start. Just check out my F# videos, maybe check out some other videos on YouTube, maybe even check out the papers on counterfactual regret. These days, you can just ask ChatGPT for a link to the paper or even an explanation. It's not that complicated. Yeah, in the spiral playlist, we also experimented with some evolutionary algorithms for optimizing neural net models. And as I said in the previous video, all that worked horribly. Pretty much everything I tried worked horribly. The only thing that actually worked well is tabular CFR and tabular reinforcement learning. It's amazing how robust and how well it works compared to neural networks. But the problem with tabular reinforcement learning is that it's not scalable. And what we want to do in this playlist is not necessarily to make it scalable, but to make it more scalable. And if we could accomplish that goal, at least we could attain the full power of tabular reinforcement learning and tabular counterfactual regret algorithm without any of its downsides. So this isn't getting ahead of ourselves. Before we go into the actual plan, I need to explain a little bit about what the Hopfield dictionaries are and how they relate to the counterfactual regret algorithm. And in fact, instead of explaining them, I can implement them in a single line of Numpy. So let me do it. I actually forgot whether I did this in the previous video, but we can do it again. It's no problem. Wait, did I actually... Oh, sorry about that. Yeah, okay, so this is the ML library. Let me just commit this. And we're going to make a Python script somewhere. Let's see. What CFR Python. I'm going to make a Python script py, and then let's see, import numpy as np. Okay, let me pause just a bit so I can install the dependencies. I'll be right back. Okay, so this is numpy installed. Now, the reason why it's still grayed out is because I think I need to select the correct interpreter in VS Code. So let's see. Let's try this one. Yeah, great. Now this isn't showing a type error. So let's see. X equals np, and then how do we create an array in numpy? Maybe like this. 1, 2, 3. I'm just refreshing my memory of. Wait, is Alt Enter not working? Okay, so this is Shift Enter. When I press the Shift Enter, I can just send all these statements to the to the terminal. So that's kind of an easier way of running it. I can kind of run individual statements with Shift Enter. Okay, good. Okay, so what are Hopfield dictionaries? They're very similar to regular dictionaries, and regular dictionaries in Python, and they're an ubiquitous data structure that's present in every single programming language. They're a data structure that's based that holds key associated to values. So in Python, we could do A, and A could be 1, and then B, 2, and C could be 3, something like that. And this is now a dictionary, and I'm not sure whether the Python actually calls these dictionaries. Oh yeah, it's a dict. So yeah, that's short for a dictionary. Some other languages call them maps. And yeah, actually, I don't know whether they're called anything other than maps and the dictionaries. So yeah, compared to arrays, arrays just use integers, simple integers as indices, but dictionaries can hold arbitrary values for keys. You know, instead of like a string here, let's see. Okay, if I try index x of a, then it shows 1. But we can also use more complex data types for keys, like is this not working? So it's something that is not cacheable. That's really weird. Okay, so I guess it's cannot cache a list. What about caching a tuple, something like ASD, ASDF? So let's see, if we try indexing into this, what will we get? So yeah, as you can see, it doesn't necessarily just have to have keys as something like an integer or a string. Dictionaries can also have complex data types that can be tuples of strings and integers. I think we could also make them like a record of, let's see. Let's try making this a record. Gonna be like this. No, it's not cacheable, unfortunately. Okay, maybe we could make it a set. Oh, so this is also not cacheable. Okay, I actually didn't know that that this was the case in Python, because if we let's say if we did it in F#, this would be in fact cacheable. I can very easily prove it. So okay, let me try. Let me make an F# script just so I can prove it. I'll pause for a bit. Okay, I was kind of going for this, but it isn't working. It's kind of telling us that a dictionary can only hold a single type, and these are strings, and this is a set of strings. So in a static language like F sharp, what we do is make a union type, and then we just string of string, and then string set of string set, and then we just wrap these in a union string set. Yeah, now we have now we can very easily put sets as keys of a dictionary. In particular, the most likely reason why this is unhashable is because sets are immutable in Python, while F sharp has immutable sets. So in fact, they're not really the equivalent type. In .NET also has like immutable sets, like hash set. And yeah, if we tried using this, we probably wouldn't be able to put them. We probably wouldn't be able to use them as a key. Let's see. Oh, we can. Oh, interesting. Okay, I'm surprised that this worked, but we generally don't really want to use immutable data structures as keys in a union type. And even if we do use them, we have to be very sure that we don't mutate them accidentally. So yeah, why is this important? Well, we can kind of we can also have when we are using tabular reinforcement learning. Being able to use union types like this means we can kind of let's see. We can kind of represent the game states using union types, in particular the action sequences. Let's see. We can kind of let's suppose we have a game trace type, and then we can kind of have like raise, call, hold, and we can also have a draw, and then we can have some kind of card type. Let's see, type. Whoops, sorry about that. King, queen, jack. And we can kind of represent the game state like this. So let's see. First, we can kind of see the player drawing a card. Let's see, draw king. Then there might be some like calling. Let's make this a raise call. Okay, just ignore what these values on the right side are. So then suppose we see the community card, and so it's the community card in something like Leduc poker could be queen. And this kind of represents every action like as a separate thing, which is not exactly what we want to do. What we'd like is to have a complete trace. So okay, let's get rid of this. Let's see. Let's put this on a single line. And this could be some kind of a value that represents all the policy probabilities or the expected values. And of course, if we have three different actions, we could let's see, type action. Let's factor this out a bit more. And then we have three different actions, so we have some kind of value for that action given this action sequence. So let's see, we have king. We have a king in the hand, so maybe raising would be okay. But we don't have a pair, so whatever. Let's make it 2, 1, and folding would let's say have a negative value, so something like that. And now you can see in this dictionary we have a game trace, a list of game traces, and we have whoops, sorry, this is supposed to be a list. Let's also make these floats. Yeah, now it's much better. So yeah, now we have the game trace. We have and we have some expected values. And using this kind of regular dictionary, we can implement tabular reinforcement learning for pretty much every single game that we can think of. If it's something like Leduc, we can use the traces there like this directly. But if it's something different, like normally call them, we wouldn't be able to use the traces directly, because they would be simply too many possible different actions. So we need to kind of make a function so it compresses the traces to a smaller number of possible states. And in the reinforcement learning literature, that is called abstraction. In Python, okay, Python does have union types, so we can also try doing something like that in Python. Okay, let me pause a little, and I'll try replicating it. This is how we could define the types in Python. They're pretty much a straightforward translation from the equivalent F# types. So, okay, so how do we put this into a dictionary? Let's see. Okay, so first these semicolons need to be turned into periods, commas. Let me pause it just for a bit so I can get this worked out. Okay, so this is an example trace, and we should be able to put a type on it. So let's do it like tuple, and then game trace, and this is float list. And what exactly is the problem? Wait, sorry about that. List float, yeah, something like that. And what's the problem now? Tuple list, game trace, list float. What's going on? Union card. Okay, let me pause so I can figure this out. Okay, I think I understand. It's not actually Python is not actually inferring these strings as string literals, so it's not really acting how it would in TypeScript. Sorry, I'm not actually that experienced in in Python, but really, how the hell did I manage to get this to work? Okay, let me ask the chatbot how to fix this. I'll be right back. Oh, I did a really good job. Yeah. This should be a list of game traces. Oh, nice. Now it's working. Yeah. I got the floats right, but I got this wrong. So this is like a key value, and then we can actually put this in a dictionary. In fact, let's split them apart. Key list float. And we can make a dictionary of these values. Key, oops, sorry about that. It should be key and then v. And let's see, what is it saying here? A dictionary key must be hashable. Really? Is this really not going to work? I mean, it's kind of weird that it would refuse an array. But yeah, unhashable type. So yeah, I guess we learn something new every day. I'm really surprised that we cannot just put something like a list of strings in a Python dictionary. And we can do it in F#. So F# is actually a lot better language to do reinforcement learning with. But at any rate, you roughly understand. You should roughly understand what I'm going for here. What I'm trying to demonstrate is that these dictionaries are used ubiquitously in reinforcement learning in order to store the tabular representations. And what I want to do is replace them with something that's called a Hopfield network. And let's do a brief search for Hopfield networks. Modern Hopfield networks. And they should probably, yeah, they were introduced in the Hopfield networks is all you need paper. And in fact, the large language model, the transformer models actually use them as their attention mechanism. But they are interesting in their own right. Let's see. In this blog post, they show some examples of how they work. This update rule with the sign is the old Hopfield network, and it's to be distinguished from the modern Hopfield network. So yeah, the way the Hopfield networks work is that you put a bunch of how do you put it, elements into it. Like this image of Homer Simpson is converted to black and white. So it's only like zeros and ones, which represent black and white images. And then suppose you have once you have a bunch of data in that in the Hopfield network, you can take some other data, like for example this image of Homer Simpson, and mask out the various values of it. And then what this network will try to do is reconstruct the data based on what's already in the network. Something like this. Train input 1, train input 2. So it has these images in it. And these are the test time images. So this is the mass test image, and for some reason it's outputting an image of Bart. And for this, it's actually outputting an image of Marge. And okay, so I think that the reason why this is happening is because they're showcasing the old Hopfield networks. If you take something like a neuroscience course, you probably have a class on the Hopfield networks, and the old Hopfield networks have a very limited storage capacity because they're using a pretty weak how do I put it, cost function or a distance function to calculate the differences between the examples. So if we go a little bit lower, I think it should probably showcase the modern Hopfield network, and this is this one, in fact. So yeah, and now it actually does good discrimination between the images and achieves the correct reconstruction. I think this is actually pretty easy to implement. Like all this seems very, very complicated, but these are just pretty much pointless math. The actual formula to implement it is just this x. This is the this is the input matrix, and then that's passed through a softmax, and this is the output matrix. Okay, so sorry about that. Let's actually implement it so it will make more sense in NumPy. All of this stuff is just confusing us. Like, I think this should be the actual image, but who knows at this point. Okay, let's do it properly. So, okay, I actually don't know how to use linear algebra libraries in F#, so we're just going to implement it in Python. Let's start a new script. Okay, actually, let me name it Hopfield network. And this is a bit distinct from a Hopfield dictionary. This Hopfield network is actually, it pretty much acts as a set data structure rather than a dictionary data structure. But once we do have a set, we can very easily extend it so it acts as a dictionary. But for now, let's just do the set first. Okay, so we have the NumPy. We need a bunch of, let's say, inputs. Then let's make these ones and zeros. Oops, sorry, I pressed the wrong key. Okay, so let's see whether this actually creates a two-dimensional array. Yeah, it does. So what we need to do is first calculate. Well, okay, let's make something like let's make an input. Okay, these are the keys. Let's make these the keys. Let's make an input. Actually, we can just make it a vector. And let's see. Let's do it like this. And you know, if we pass this into a Hopfield network, it will just reconstruct the original thing. So let's add a few more zeros to the end, and this is going to reconstruct something like this. So ideally, suppose we passed an input like this into a Hopfield dictionary, then as you can see, the closest match would be this one. So this is also what it should output. So how do we do that? So first we have to essentially multiply the keys by the input. Let's see. Keys. Okay, how do we do a matrix multiply in NumPy? Oops, matmul. Oh, nice. Okay, so we do keys and the input, and will this be right? Yeah. So this is we get an array with three elements in it, and as you can see, this is the closest match to the first one. It has a it has a one positive hit. So this row in the keys array has a score of 1, this has a score of 0, and this also has a score of 0. So what we have to do is pass this through a softmax. So let's see, np softmax. Okay, so I'm going to have to ask Perplexity whether NumPy has a softmax function. Does NumPy have softmax function? That's really the main thing that we need. Okay. Yeah, let's just copy paste this. This is just a demo, so I don't really care about the efficiency. So, okay, if we do this, yeah, then we actually get a probability distribution. And the first element has the highest probability. And of course, as you can see, 57% isn't really that great. And in order to actually get something like most of the probability on the first element, we have to multiply this result by a scalar. And in machine learning literature, this kind of scalar is generally called a temperature. So we can actually divide by temperature, and we can kind of set to 0.1. Oops. Oh yeah. So this is like 99.9%. Okay, let's make the temperature like 0.5, because the softmax values have exponential scaling. Okay, let's see. How about this? Yeah, this is pretty much the same what we had before. Let's go with this. And the reason why I am dividing instead of multiplying, if you think about it, it's pretty much the same thing. But in the literature, they tend to divide by the temperature. So that's why I also do it like this. So yeah, so we have this first element, which has a 99% probability. And in order to get the reconstruction, what we also have to do is multiply by the keys array, by the original keys array. So let's see. We have to do an np mathemol. So what do we do here? I guess we put in keys, and we're probably going to get an error. I bet. Okay, what's going on here? Oh yeah, this is actually correct. I thought maybe that we'd need to transpose the keys, but I don't think that's the case. Let's see. If we do this, yeah, now it's complaining that there is a mismatch. Yeah, so yeah, this is exactly the formula for a Hopfield network. If we make the if we make the temperature even lower, like 0.1, let's see, we're going to get. Okay, this is kind of hard to read. So let's also try to round these results. Let's see, np round. Yeah, so as you can see, this is pretty much the original input array that we have now. And suppose if we want to use this as a dictionary data structure, it will be very easy to actually extend this. So let's see, we have the values. Let's put in some values. Really, let's just copy paste this. Values. We're just going to remove these. And now, instead of multiplying the original input with the keys, we can multiply it with the values, and then we'll actually get just the reconstructed values. We also need to remove some elements from the input. Yeah, this is it. And if we, for example, do like 0, 1, Yeah, then we get these this middle values array. Suppose we do something like this, then we're going to probably get a mix of both. Let's see. Yeah, because we're doing a rounding, it's kind of hard to understand what this is doing, but it should. Let's see. So yeah, so the first element is like almost one, and this is exactly 0.5. And the reason why is because the probability mass will be perfectly evenly split between these two inputs. Like this one will be 50%, and this one will be 50% for the given input. This one is 0. So 50% of this then 0.5 plus and this is the result that we get here. Roughly, very close to what we get here. Like if we reduce the temperature even further, yeah, now it's this exactly. So this is how the Hopfield dictionaries work. This is the one line that I was talking about. It's pretty much exactly this. These are the Hopfield dictionaries. It's just a matrix multiply, and then that's being passed through a softmax, and then another matrix multiply to reconstruct the actual values. And it has some interesting properties if you think about it. Suppose so suppose we have suppose these are states in a game. When we use a dictionary, we can translate each of the game traces to a single integer that's unique, and it can be represented as a one-hot vector. We can the main property of the Hopfield dictionary is that it can average out the values between the different states. So this can be just binary vectors. This can be vectors of arbitrary values. Like this could be 10, 50, 0. Okay, let's assume this is like a raise. So this is 10, calling is 20, folding is -10. And in this situation, maybe raising would be 20, calling would be 10, and folding would also be -10. And let's say raise, maybe this is a game state where we have a really good hand, and we have the nuts on the board. So raising is very positive, calling is just 10 in expected value, and this is also 10. And suppose we have this input. If you run it through the Hopfield dictionary, we get this reconstruction. And what we can do, if you wanted to actually update the values here, it's not like in tabular reinforcement learning when we have a dictionary and then we have a mutable array in it. Instead, we just add an element to the dictionary with the same key. Now, let me just remove these comments. And as you can see, we have roughly the same. I mean, we have exactly the same value here, so we're going to get the same reconstruction out. If we, for example, change this to something like, let's say 40, then what we would assume that we're going to get the interpolated values for the second element, in other words, 30. And this is exactly what we get. And as long as if you have some reinforcement learning algorithm, As long as the updates average between the previous and the current state, we can actually use the Hopfield dictionaries to re-implement the algorithm using it. Let's move on. What I want to do next is sketch out the counterfactual regret updates and show that they can be implemented in both. We know that they can be implemented using dictionaries, but I want to also prove that they can be implemented using Hopfield dictionaries. I can't really do the full counterfactual regret algorithm here because it requires requires itself to be embedded in a game. It requires like a model, and the counterfactual regret algorithm is just an inference algorithm, so it cannot really function without a model on below it. So let's see. I'm going to pause a little here and maybe implement some of the things out so you aren't watching me doing everything step by step for the sake of time efficiency. For the ease of presentation, we're going to be using 3 separate dictionaries. When we get to the actual implementation of the Hopfield dictionary in the future, these 3 will be fused into a single dictionary for the sake of efficiency. But right now, since we are just sketching things out, it's easier to use separate dictionaries. And of course, this isn't a Hopfield dictionary, but a regular dictionary, and I'm just using strings to represent the different states that could be there. So the counterfactual regret algorithm doesn't just have expected values like TD learning or SARSA. It also has the policies, and not just one, but 2 of them. This current policy is the policy that's actually being used during training to actually play the game. And this average policy is averaging out the current policies. As the game is played on something like poker or other kinds of games as the game is played in a 2-player setting, this current policy will tend to oscillate between extreme values and won't really converge to a stable value. Instead, what will happen is that if we average out the current policy, the average policy will in fact converge to the optimal policy. So that's really the big deal about the counterfactual regret algorithm, and one of the main differences in how it differs compared to regular reinforcement learning algorithms that assume a stable background. The regular reinforcement learning algorithms like Q-learning, TD learning, they all assume that the game is static and that the agent can be run to find the optimal values without, for example, the other agents in the environment adapting to it. That's not the case in poker, so we need the counterfactual regret algorithm for the sake of that. And this current policy, it's actually it does represent unnormalized values. So if we have something like 10, 10, 10 here, let's just put in 10, 10, 10 everywhere. These are supposed to be the values for the probability distribution. In fact, some of them can be negative. So how do we get the actual probability distribution from that? So let's make a helper for it. Get prob. And we're going to pass in a numpy array, np in the array, return. Yeah, we're also going to be returning an np in the array. We're not going to return the same array. Instead, what we're going to return, first of all, we need to clamp all the values in this array to if they're below 0, we need to clamp it to 0. So it's kind of like a ReLU function. Let's see. Does the NumPy have a ReLU? Maybe it has max and the max 0 and x. Yeah, maybe that's what we need. So let's apply that, and then what we have to return is x divided by sum of x, np sum of x. So let's try using this, and then we'll index into the current policy at state A. I want the integer scalar arrays can be converted to a scalar index. What exactly is the problem? Oh yeah. It's not taking a max between a constant. It's just finding the max of every element in the array. Let's ask Perplexity how do I okay, how do I do a ReLU operation in NumPy? Oh, so it's like this. Okay. I guess np max and np maximum are separate things. So we just do a ReLU. Oh yeah, nice. And we get the probability distribution based off that. One other problem is that you know the policy can be all 0, and in that case, yeah, we kind of we have problems. So let's see, s equals np sum, and if s not equal 0, else oops, this isn't F# but Python, else we have to create a uniform distribution. So how do we do that? We're going to do that by let's see, np like zeros empty full like x, and the fill value should be x. Let's make it the length of x. Yeah, something like this. Oh no, this wasn't right. Let me think. Where did we go wrong? Now let's print out the. This should be 0.33, I think. Yes. Why is this not working? Yeah, because it's probably returning an integer array. That's what the problem is. So okay, let's put the types of all the arrays here. The type equals float. Would that work? I mean, if it doesn't work, what we are going to do is just change it. Oh, okay, it works. Nice. Yeah, it's perfect. So we have this function to convert these unnormalized arrays into probability distributions. Oh wait, I should be using S here. Sorry. This is for efficiency. And it's Python, so we don't really care too much about efficiency, but I still, don't want to waste cycles meaninglessly. Okay, so we have a way of getting the probability distribution. These expected values, these aren't the probability distributions. So what we have to do is implement the counterfactual regret update. And the actual algorithm implementation is significantly more complex because it has to be embedded in some kind of an interpreter for a game. You can see how it was done in Spiral, in some of the Spiral videos. You can also see how it was done in the F# series. But over here, we aren't actually going to have a model. Instead, I'm just going to demonstrate how to update the state. Let's see. Let's name this CFR update, and this key is just going to be a string, and expected value is just going to be an ampere array, and the array. So first, let's get the A, C, and E. C and E. That's going to be the average policy. Current policy. Expected value. Values, I mean. So we have these three arrays. What we have to do next? Okay, so we have to assert that the expected value, the length of the expected value equals the length of E and also in a real implementation, if the key isn't present, we have to add a default state. So now let's make a little get function, and so we already have the key. So what do we do? Let's make this a dictionary dict. And so if D contains if key in dict, then we can just return the key. Oh, whoops, not key in dict, but key in D. Else, we're just going to return something like np empty like. Sorry, no, let's just make it np array 000 the type equals float. And we can just get the average policy, get the current policy, and get the expected values. Okay, not bad. To do this. So yeah, we have to work towards towards actually doing the counterfactual regret updates. Besides getting the key and the expected values, we also need the path probabilities. we need the own path probabilities. We need the path probability of opponent, and we also need the path probability of the sampling. This sampling path is the actual path that was taken in the model, and it reflects the actual choices, the actual probabilities of the choices taken. And this path probability of the self, that will be the path probability if we took all the choices according to the current policy. So, for example, in the counterfactual regret algorithm, it's true that we have the current policy, but we can also use something that's called a sampling policy, which can even be uniform. It can be, you can just assign equal probability to all the actions. And we can do some trickery with importance sampling to make sure everything kind of meshes together. If you never heard about importance sampling, I kindly suggest that you take the time to learn what it is. Like, just ask Perplexity, what is importance sampling? All the Monte Carlo algorithms use it. It's a very important concept. It's a very important concept in probability theory. And okay, this is a very complicated explanation, but basically, it allows you to use a separate probability distribution to do the sampling, and then adjust it so it's so you cannot get the same results as if you were using a different probability distribution, like the current policy, in order to get the expected values as if you were using the current policy, even if you were using a different policy for the sampling. So we need these three floats. Okay, and now that we have these arrays, we need to get the current policy probabilities. Let's just make it probes, and then get. And these are the actual normalized policy probabilities. They sum up to 1. They're all positive. And what you have to do, these are the expected values. Yeah, let's make it like this, new expected. And we have to do some updates. Okay, first of all, we need to, we have these two things. So let's backtrack a little and ask ourselves, how would we update the expected values in something like a Monte Carlo counterfactual regret algorithm? So we could just, okay, as a first step, we need to add the new expected values to the old ones. So let's see, new E equals new expected values plus E. And we'd assign them, we assign the expected values to that. Let's see, expected values E equals new E. So let's see what happens when we try doing that. Let's do a CFR update. The key is going to be state A. The new expected values. Okay, let's make them something crazy, and we need to make this a numpy array, like 100, 100 minus 200. And let's make the d type a float. And we need the path probabilities. Maybe we can just put these all as one. It doesn't really matter right now. And if we run this, okay, obviously nothing is showing up. But if we print out the expected values afterwards, yeah, as you can see, this crazy value got added to the state A. And that's not really an averaging operation. So how would we average it out? Well, I mean, one option would be just to use a queue, but we can use a simple moving. We can use the simple moving average formula to get the same effect. So let's add a little mutable variable here, which will be the count. C equals 1. And let's make this a float. At the very end, we'll actually update the count. But over here, we're going to take a convex combination. Let's see. New expected values and old. Okay, let me ask Perplexity what the simple moving average formula is. What is the simple moving average formula? So annoying with these pop-ups. Yeah, so it basically takes all the values in the array and divides them by the number of elements in the array. But there's also a way of a different formula that actually can update them incrementally. What is the formula that does incremental updates? I know I have it in my mind, but I cannot remember exactly. Yeah, so it's A plus 1 minus A. So it's 2 divided by n plus 1. I think this is an exponential moving average. And okay, so let's see. If we set the alpha to 1 over c, this is going to be alpha plus. Okay, actually, let's put the old value on the left and the new value on the right. So this is 1 minus alpha plus, oops, times plus alpha times new expected values. And we're actually going to start off the count at 2. So otherwise it won't really, otherwise it will wipe out the old value. I mean, we already have like some data in the arrays, so we can kind of assume it starts at 2. So let's see. That's 1937.9. Okay, so does that make sense? Let's see. We have we're going to add this. And then we're going to divide it by 2. Oh, no, it didn't work, unfortunately. Um, so this should be 1/2. Let's try this again. 1937.9. Okay, where did I make a mistake? Let me pause just a bit so I can figure it out. Oh yeah, I figured it out. And the problem is that I'm shadowing the count with this temporary local variable. I guess that's why it's not a good idea to use short names for globals. Count. Let's make it in global count. Let's make it 2 again. Okay, that's one error fixed. Now, suppose we try making 2 separate updates. Like, okay, let's just update it towards towards the same value twice, and we'll see what happens. And we'll also, yeah, let's also copy this. And we'll take the average of these 3. Let's see whether they come out the same. Yeah, they do. So as you can see, we're using the simple moving average formula to update the arrays in place. And if we use the Hopfield dictionary, it would automatically average out these 3 values. And we're going to demonstrate that in the future. But for now, I want to complete the entire counterfactual regret update. So, okay, let's leave this update for the end. What we have to do now is calculate the mean value of the expected values in order to actually calculate the update for the current policy. So we'll leave this for the end. This alpha, okay, I guess we can move it to the start. Mean expected mean of EV. And what we'll do, we need to take the expected values and then multiply them by the current policy probabilities. Oops. Okay, we have the current policy probabilities. That's a probability distribution. We just need to multiply them by this and then sum them up. And I think Numpy probably has a dot product in there somewhere, so we can just do this. Okay. Now we have this mean expected value. In order to actually calculate the update, we have to subtract this mean from the expected values. So current policy update mean expected values minus mean of EV. And now what the current policy would be is, let's see, the update for this would be, let's see, this would be C. This would be the current policy update. And for the average policy, let's see, average policy, I guess, yeah, this could be A. This needs to be A, definitely. And this thing here, let's calculate the average policy update. That would be something like we need to actually take the updated current policy, okay, like updated current policy. We need to turn it into a probability distribution again. Oops, wait. Mm. I'm just trying to think a little, think of a way to organize this a bit better. These are all the updates at the end. Let's see. XML updates. All of these steps are immutable. Yeah, I think this should work. We'll have to actually try them out to make sure that it is working correctly. And we're going to put in some print statements to really get a sense of how all of this works. For now, let's just run it to see whether there are any type errors. Okay, let me just get rid of this. Let's also print out the, let's see, the current policy, the every step. The current policy is 10 10 minus 10. It's 5 5 minus 155. Okay, now we have to figure out whether this makes sense exactly. So this is what it is at the start. Yeah, then it goes more into the negative. Yeah. These two are the same value. So yeah, it makes sense that at every update states these will also be the same. Mm. Okay, let's calculate the mean of expected value, and let's also print out, let's see, the current policy probs, and this is going to be EV. Well, let me just do this like so. Current policy update. Now let's try running this. So this is the beginning state. The current policy probabilities are all 50-50 between the first and the second action. Let's see. That doesn't really... Oh yeah, that does make sense. So let's see. The mean of EV being 50, does that make sense? Well, this is 0.5 times 100, 0.5 times 100, and 0 times minus 200. So yeah, given the current policy, the mean expected value is 100. The current policy update, really? Does this make sense? Oh yeah, so I subtract minus 100 from, that is the mean EV, minus 100 from 100, minus 100 from 100, and minus 100 from minus 200. And yeah, we get this. And in fact, this is the correct current policy update. Then that gets added to the current policy. So yeah, what happens is that the current policy just gets more and more negative. And yeah, that's how it should be. In addition to, let's see, where is the current policy? In addition to just using the new expected values minus the mean of the expected values, for the update to be correct, we have to take into account the path probabilities. So for the Monte Carlo counterfactual regret algorithm, the update is this. It's times the path probability of the opponent and divided by the sampling probability. So in other words, we divide out the total path probability up to that point, and just add the intended path probability for the opponent, and that would be the current policy update for the Monte Carlo variant. Now let's see what the actual what the average policy ends up being. Let's just comment out these print statements. Now let's see. It ends up being 0, 0, 0, 25, 25, 33, 33. And of course, this is the unnormalized probability. But if we get the normalized probabilities, what happens then? Okay, let's just print out for the state A, state A, state A, and get so it's uniform at the start, then 0.5, and then it's also 0.5 here. And I want to point something out. For the actual policies, using a moving average isn't at all necessary. It's just a needless division. To prove my point, what exactly happens if we, let's see, if we remove this and this, and if we also remove yeah, we get pretty much exactly the same values because they get normalized at the end. The same should go for, let's see, the current policy. If we run this, 0.5, 0.5, 0.5. Okay, let's make it a little bit more interesting. Let's make this 200, 200. Oh yeah, then now it becomes 1. Okay, suppose we do 100 and then 200 here. So I'm not sure exactly what we're looking at here. Let's see. If we run this again, minus 15, 35, 35, 35. So yeah, so it goes back to 35. Can we suppose we did it like 170? There, and if we put back these, get probe distribution, 0.5, 0.5, 1, and this is like 61%, and this is 38%. And if we put back these alpha values, I want to prove that the moving averages aren't even necessary for these updates to work. Wait, also I need to put it here. For the current policy updates. We should get exactly the same result, and we in fact do. So what I've done here is proven that the moving average updates aren't even at all necessary for the CFR policy updates, and they really make no difference because of the normalization that's being done when converting the unnormalized distribution to a normalized one. Now, for the moving averages, it does make a difference, I think. Let's see. If we just added it to the moving average, where exactly is it? Oh yeah, so this is. Okay, let's do this at the end. Put it at the end, and if we remove this from the expected value updates, yeah, I mean, actually, it won't make a difference because nowhere are we actually using the old expected values. That was silly of me. Okay, so I've had some time to think, and let's fix this nonsensical expected values update. Right now, it's not really even close to how it would be in the multicolored CFR update. In the multicolored CFR update, you wouldn't get an entire array. Instead, you would just get the index and the reward. So let's adjust the function so it does that. So let's do action index. Action reward. This is going to be a float. So we also need right. Obviously, we can't pass an array. So let's make this reward for the first action. Let's make it 100. Actually, let's make it for the second action, and it will be 150. And this is going to be, let's say, 0, 170. So typically in the Monte Carlo CFR algorithm, this new expected values array is calculated from the old expected values, and the action reward is added. I mean, it is also added to it at that particular index. So let me show you how it is done. Okay, new expected values. And I'm not going to do it all here. Instead, I'm just going to factor it out into a function because it's going to be crowded otherwise. Let's see, expected values. I guess we will factor it out somehow. No. Okay, def. Just copy paste this. Oops. Yeah. Oh yeah, we also need the key. Let's do the key. Now we'll get the E. Actually, instead of just getting the key, let's just also get the E. And np and the array. Passing the E. Return. And of course, we want to just return this E. I was just the reason why I did that is just so I can make sure that because I saw the type error here, just to see whether that gets rid of it. Now, yeah, we have to iterate over this E array. Let's see. These are the expected values at the key. And let's make the E np0 like expected values. And what we'll do after that is iterate for in math. We want to iterate over all the elements of this array. Okay, so I guess range len e. Okay, so we have the index, and we have basically two different cases that we need to take care of. So if I equals action index, then do something else, do something, and that something is let's see. Okay, let's take care of the else first. So this is a very easy. I equals expected values I. Oh, that's simply it. And no, it's actually not just that. We also need to factor in the path probabilities. Okay, let me think. Path probability of self. Oh yeah, we also need we need the action. We need the sampled action probability, and also the path, also the probability of the action being selected. Okay, I'm going to have to add some more variables. The action probability is not necessarily the path probability. Rather, the action probability is just the. I mean, we can get it from the current policy. So let's do that. Action probability equals let's see, current policy probabilities, and we'll index it with the action index. And we assume that this is a float. And there's also the sampling probability of a particular action. And let's make this, let's assume this is like a convex combination of the action probability. Okay, let's do it something like 1 minus 0.05. Let's make it like, times 0. Well, let's say the probability of resolving a random action is 0.20. Sorry, let me just pause so I can think about this. Okay, I thought about this. Basically, let's say we have an uniform distribution. Okay, we have the current policy probabilities. This is a discrete distribution that has very specific probabilities for each particular action. Let's imagine we also have a uniform distribution of uniform probabilities. Uniform probs equal that will be np like, and it has to be similar to the current policy probabilities, and it has to be 1 over the length of basically 1 over the length. Wait, why is it? Okay, like this. And suppose we have like 3 actions. What this will set is the probability of every action to 1/3. So the current policy probabilities will have pretty much arbitrary probabilities for a particular action. It might have in a particular state, it might have 50% call, 50% raise, and 0% fold. But the uniform probability will have 1/3 call, 1/3 raise, 1/3 fold. And the sample probability, we just to get the sample probability, we just interpolate between the uniform probability distribution and the current policy probabilities. So let's make the epsilon. Let's set the epsilon to something like 0.05. Oh yeah, this cannot be a float. I mean, we already sampled it. We already sampled the action probability. So let's do it like this, and then plus epsilon times uniform probability at that particular index, action index. But we already know that this is just 1 over the third. So we can just set this to uniform probability and this is basically our sampling probability. And this is just to indicate that we can have a different sampling probability in order to reduce the variance and in order to encourage exploration. because reinforcement learning agent can get stuck in a local minima, so it only does a certain subset of actions, even though maybe some other actions which have a probability of 0 might be more optimal. So that's why we might use a separate probability distribution for exploration. And typically in the literature, you'll see something like this, where you have a current policy probability, and you also mix it up with the uniform probability, so yes, in order to inject some randomness into it. So okay, so we have the sampling probability and the action probability. Let's see. Values, yeah. Let's action probability and sampling probability. And as you can imagine, we have to basically factor out the sampling probability and multiply by the actual action probability. Oops, let's put it here. Yeah, is this right? No, it actually isn't right. Because we haven't actually selected this particular action, so it makes no sense to cancel out the sampling probability. Rather, the actual formula is more like this. Let's see. We have the reward. Let's see, where's the reward? The action reward. Minus the expected values, minus dv. Let me just factor it out. Minus the predicted EV. And now this we have to multiply by the action probability and cancel out the sampling probability. But also in addition to that, we have to basically add this part here. And in case you're wondering what this is, maybe take a look at my F# video, but I'm going to write it out simply what this represents. This is this action reward. Let's name it R. And for that, we are subtracting the expectancy of some other variable. Actually, no. We're subtracting this, and there we're adding the expectancy of some baseline. Basically, this is the actual reward, and this I here is the baseline. And as you can see, these two y and the expectancy of y cancel each other out over a long period of sampling. And when it's done like this, it reduces the variance of the algorithm, and it improves how fast the algorithm learns. You can see a better explanation in the F# video. So kind of went into some detail. Like if you assume that the action probability is equal to the sampling probability, let's assume it's 0.25, then this particular action will get selected like 25% of the time, and it will get added to the action reward. But the other 75% of the time, when the other actions are selected, only this expected value will get propagated to from this as an unexpected value as from this function. And yeah, admitting you have to basically stop here and really think about it, but it does make sense if you kind of simulate it uh, uh, over over a dozen different over over a specific number of steps. So okay, now we have the new expected values, and we get that from the action probability, from the sampling probability. And we're kind of assuming that the epsilon epsilon is in fact what the action has been sampled from. I mean, it kind of matches the distribution, What I want to say is that this epsilon, we're kind of getting the sampling probability here using this epsilon, and we are assuming that the action in the actual algorithm will be sampled using this exact same epsilon. So okay, now we have this. Let's see. We have the new expected values. Yeah, I was supposed to basically prove that this doesn't really make sense, I think. And okay, let's do that now. Like, let me first bring back the alpha. And this update is wrong, regardless whether we have the alpha, this moving average to the division or not. And it's going to be pretty obvious why very quickly. Let's see. We just need to figure out whether this is running correctly. I mean, okay, we're kind of looking at the current policy, and instead what we have to look at is what is the expected values. Okay, so let's see. 75, 83, and then this is 5, and okay, what the hell is this? Okay, let's just set this to 0. Who cares? Okay, so this is 75 now, and this is 50, and yeah, there's something wrong. This doesn't really make sense. I mean, okay, over here it does make sense. It's 0. It's all zeros at the start. Then then the first action should get updated to 150, and then maybe I don't know. Why is this like this? Why is this like this? Oh yeah, maybe because I have this sampling probability. Okay, let's set the epsilon to 0, so the sampling probability is the same as the action probability. This is what's causing the confusion. Okay, yeah. So we have all zeros at the start, then it gets updated to 150 and divided by 2. Then this first one should get updated to 170, but we're getting a nan, and that's not good. Okay, so let me think about this for a bit. I guess we're going to have to do some debugging. What I expect to see here is 170 divided by 3. So, okay, let's make it like something that's more easily divided by 3, like 225. Which is going to be, what, 75? Let's see. Okay, let me print out everything. The action probability. Let's just print out everything one by one. That's the easiest way to do things. Just print it out. Let's see. Action probability, sampling probability. This isn't good. Right. Yeah. Yeah, I mean, but the first and the zero task action should be positive, so this is very weird. Well, let me think. Okay, this is 0, 0, 0. Right, on the first iteration, the action probability is 0.5, sample probability is 0.5, the action index is 1, the action reward is 150. Okay, that makes sense. Okay, so this cancels out. Let's print out the expected value. All right, right. After this update, what happens is that the action probability of the first action gets set to 0. And because of that, also the sampling probability is set to 0. So it cannot really possibly be the case that the first action has ever gotten selected. Okay, maybe we can set the epsilon to something like whatever. Let's just do this. Maybe like let me just pause here so I can think about how to do a better example. Okay, how about this? What I simply did was go here and then ramped up. What I did was go here and then ramped up the values to 100 for the current policy. That way, even after an update, it will still retain some positive value, and it won't. And the probability of the first action won't go straight to 0. Like you can see here, it goes to 0.125. And you can see it's 0, 0, 0. This is expected values array at the start. Then at the first update, we ramp it up to 150. That gets divided by 2. And then what I want to do is update the first action. And that gets updated to no, this isn't right. This is supposed to say 50 instead of 53.125. And I think what I did wrong was probably this. Let me think about this some more. We can replace this with just EV. Sorry, viewers. I've gotten confused, and I've actually done this incorrectly. This doesn't make any sense. I had to look at my old code base here to get some clarity on what's going on. So yeah, the action probability is not something that we need here. In fact, it only gets applied in a different step. And even if it does get applied, there isn't we cannot apply just the action probability for the sampled action, but for that specific action at the index. So yeah, this isn't supposed to be going here. Yes, and this is how it's done. And okay, so we have these expected values. So that's the previous thing. This is the new expected values. And in fact, we are going to be doing the update based on this array. But we're going to be doing the update based on just the reward. This array is just for calculating the policy updates. Mean of EV. Yeah. Okay, this all makes sense. And for updating the expected values, we actually just need to add the action reward at the action index. So that's basically it. So let's think. How are we going to do that? Was it like this? E new np copy. We're going to copy. We're going to just copy E, and then at update E, we're going to at the action index. We're going to just add the action reward. And if we kind of, yeah, if we basically interpolate no, sorry, we have to make it zeros like. And then we just put in the action reward at the specific index. And we also rename this to E update. This is E plus E update. Yeah, this is roughly how I wanted to do it. So let's see whether I can actually run this properly now. It's kind of now that I think about it, it's kind of weird that it's like this. But this is how the expected values for the policy updates are supposed to be calculated. And if you imagine that there isn't a baseline, then this important sampling adjustment would be necessary to do the updates properly. It would just be action reward divided by the sampling probe, and this EV, I mean, this other case would just be 0. and yeah, that's how it. Then that will get added to the current policy update. So let's see. Let's run it. Sample probability, action index, action reward. It's a 0, 0 at the start. Then the new expected values are 0, 30, 0. Where's that getting printed? Yeah, so this is getting added. So it's 0, 0, 0 at the start. That gets divided by the sampling probability, which is I think 0.5. Yeah, I know that the actions. Yeah, it's a 0.5. That divides the action reward. It gets added to the new expected values. That is what gets used to update the policy probabilities. And the expected values, that just gets added as it is. Yeah, but in that case, we have the same issues all over again. So let's ramp up these probabilities. Here is 0.5, gets 30, 0.25, actual index, new expected values. And it's so high because the sample probability multiplies it by 4, so it ends up being 900. But the expected values end up being relatively subdued. Does this make sense? Yeah, in fact, I was going to say that this shouldn't make sense because this is now 50, so it keeps decreasing, and this is now at 2 to 5. But you'll notice that the ratio between them is actually the same. It's like 3 to 2. So it actually, so the expected values do keep the ratio, but they don't keep the constant value. Even so, that should still be. It should not be correct. Basically, imagine if instead of just this being divided by 3, even though they keep the constant values, imagine, for example, the count gets up to something like 1,000 or a million. Then this expected values array will only have very small values. So this EV will be very small. And this action reward will actually be the reward that you get at the end of the hand. So you can very clearly see from that if if the average reward for giving a hand is between 1 and 16 or something like that, and this EV is in the 0.0001 range, then using it won't make any sense, even if the ratio ends up being correct. So even if for example we didn't do that, and let's say we just remove the alpha, even if we didn't have any averaging, it would still be wrong. Why? Because suppose we do it like this, the previous value would just get added to the newer value, and so the expected values would just keep growing indefinitely. So if we are subtracting with 375 here, that might simply be too large. And it's actually very easy to fix this. That's instead of using an array like this, we need two arrays. One is to call the numerator, and the other is to call the denominator. And what I mean is something like this: num, and then how do we get the expected values array? Expected values for given state for given key. Oops. We just return expected values numerator for the given key divided by expected values for given key. And you know from basic algebra classes that any number x could be equal 8, a cross b, 8, it could be a divided by b. So x divided by x, no, sorry, x times a divided by a is also x. So sorry, no, I'm not explaining that properly. Let me just pause so I can think about it a bit better. Yeah, basically, forget this explanation. Imagine we're doing something like a moving average, and we don't have all the values right there. I mean, one way is to do it with a count and do this convex update with the alpha. Another is to just keep track of the counts and they divide them all at the end. Like, suppose we have an array A, 1, 2, 3. And then as we iterate over it, for I in A, we also keep something. We can keep a count at 0. And we can keep, we can start the sum. So let's rename this to x and l. And at every iteration, we increment the count by 1. And we also increment the sum by x. And if we run something like this, let's actually print out x and c. What's going on? Yeah, let me try putting this in a script. What the hell is going on here? I have no idea. Script 5. Okay, this works. So you can see the sum of this array is 6 and the count is 3. So if we divide 6 by 3, we get 2, which is exactly the average of this array. One other, instead of keeping the count like this, we can also put this as L num and L then. Let's put this like this. Let's actually zip these two arrays. Zip. X num x then num plus x num. Then. And if I did this correctly, we should get pretty much the same result as before. Yeah. Let's wrap this. We'll also don't num divided by then. Yeah, okay, perfect. In fact, let's split this into two different print statements. It's kind of ugly like this. Um, so what does this give us? If we keep track of the counts, then it doesn't really matter if they get averaged out. Suppose let's import numpy, and we'll turn these into numpy arrays. Import numpy as np. Let's turn this into array. And we actually don't even need the loop anymore. We can just do nom equals lnom sum l then sum. Yeah, pretty much the same thing. But let's suppose we do something like, let's suppose we multiply this lnom by 2, and this also by 2. We get exactly the same result at the end. So it doesn't really matter if we do a moving average update at the end, because we're keeping track of the counts, so we can very easily make sure they end up being well, what we want them to be in the end. Also, this technique has some interesting aspects to it. Like let's say we multiply this by 2. We also set this to 2. As you can see, if we can also use this technique to weight some of the other elements more heavily, and also bias the and also bias it towards a certain more recent value. For example, exponential moving averages kind of work like this. You weight the more recent examples more heavily. Let's see, put 1 to 2. And you also reduce the weights of the older examples. That's because at every update you end up multiplying the older values with a constant that is less than 0. So that's also one way to think about exponential moving averages. Let's go back to this. And okay, we now have to do this. I'm just not sure how exactly we could deal with when this whole thing is 0. I mean, when any of these is 0. Let me think. I mean, I can kind of add a very small value to this. It's kind of like a hack, but let's see, 2 to the power of minus 30, something like that. Now, even if it's 0, it will just end up resulting in 0. Even though personally I don't really like this kind of technique. Let me ask perplexity. How do I convert nans to 0? In a numpy array, how do I convert nans to 0? In fact, is there a way to do safe division so that when the denominator is 0, it gets the result is also 0 instead of nan. Nam to nam. So there's this where thing, really? I mean, yeah, we can try this out. Why not? I didn't know that NumPy had this. Return the AB equals we don't need the out. We do need this where, and so this will only do the division where a is, where b is not 0, and otherwise I assume it will return a, which will also be 0. I mean, that's a decent solution. Like if b is 0, then a will also be 0. I mean, the element of a will be 0. Um, yep. So because of passing the key, we're here. And when doing the update, we have to do what exactly? Okay, so this is just the denominator. The numerator. Okay, let's do it like this. And we'll also put, we also have the denominator, and that will be, what we'll do at the action index is set it to 1. And now we'll do let me do some renaming for clarity. Rather, no, let's keep it as it was. But this now needs to be a bit more complex. We cannot just take it as we want. Yeah, so I think this should be right now. So we can try out whether these expected values stay constant, and we can also combine them with the moving average updates, but it shouldn't matter because the moving average updates will end up multiplying both the numerator and the denominator by constant, so they'll end up being the same thing in the end. Let's try it out. So this is 100, it's 0, 150, 187. Does this make sense? Let's see. 150 plus 225, and all of that is divided by 3. No, wait. It's not divided by 3, but it's divided by 2. And yeah, that's 187. I mean, the denominator starts at 0, then it goes to 1 after this update, then goes to 2 after this update. And that's the correct way to think about it. And you can see that the midpoint between 150 and 225 is this number here, 187.5. And if you look at, okay, let's print out the actual denominator. I should have I should have just put the numerator at the top and the denominator at the bottom. And thankfully it was easy to swap. Okay, at the start both are 0, 0, 0, 0, 0, 0. Then 150, 1, 375, and 2. And yeah, this is how we can do the value updates. And even if in something like a Hopfield dictionary, this would end up being valid counterfactual regret updates. If in a Hopfield dictionary, we'd have something like a we'd have we'd have an averaging effect for the values under the same key. Zero 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 at the very start. Then we have this the halving because of the moving average update. But as you can see, 75 divided by 0.5 is exactly 115. So there are no problems here. And this is 125, and this is 2/3. And 125 divided by 2/3 is 187.5. We ended up not needing the path probability of the self, but that's fine. This is correct now. We can comment this out. So all of this is going to have the pretty much the same results, regardless of whether if in a Confluent dictionary there is a kind of division going on, because it has, let's say, 3 or 4 different keys, and after a softmax gets applied, the 3 different keys get assigned 1/3 probability each, and then get averaged out. The updates will still work. With this out of the way, hopefully you can see now that the tabular representations can be. I mean, hopefully you can see that the tabular counterfactual regret algorithm can also be implemented with moving averages, with really without any difference in functionality. What I have to do next is simply prove that the same can be implemented using Hopfield dictionaries, and then we'll be able to move on. So how exactly will we approach this? We can close this, we can close this, we can close this. So we have the Hopfield network. Okay, let's copy this. So we have, let's do a little bit so we can actually factor this out. There. Let's do a key, and that's just going to be, let's do an input, np in the array is np in the array, values np in the array. And we're just going to return this thing here. I can just do copy and linked input keys values. Okay, we can just put in temperature at the end, 0.01. I can put this at the top here. Let's see, does this run? Yeah, it runs. And we have the Hopfield dictionary here, implemented right here. And we can just copy paste it into CFR sketch HD. So now instead of having this average policy, we need to turn this into Numpy arrays. Okay. Np array. And this can just be 0-length arrays. No, in fact, they can't. Yeah, I actually need the separate arrays for the keys and the values. So yeah, so these are average policy keys. And what? And this is going to be 1, 0, 0. And the values will be just 0 everywhere. Yeah, we also need to put in this d-type float. Let's copy the current policy. And we'll just put in 300, 300, 300 everywhere. Grant. So we also need something like this for the expected values. Expected values. Okay. So when we're getting the expected values, now it's going to be a bit different. We basically have to apply the Hopfield dictionary. This key is the input. So let's see. Open dictionary key. Let's put it on like this. Expected values num is expected values num values. This is going to be np and the array. Not bad. Now we have this. We don't need the count, and it's going to be done pretty much automatically. Getting the probability distribution, all this is still useful. Calculate the expected values. Yeah, I guess this still makes sense. We don't need the alpha. We don't need the epsilon. Yeah, but this is no longer a dictionary. We need to get the average policy. Okay, so keys values. NP and the array. NP and the array. Average policy, keys, average policy, values, current policy, keys, current policy, values, different values. Let's see. Yeah, we're going to have to. Okay, no, this isn't right. Let's do a Hopfield dictionary. I don't know if it cannot find a match. Yeah, we cannot just pass in zero. We won't really know whether it's zero or not. So I guess it's going to be the average of pretty much every other value in the tensor. So let's see. Okay, Hopfield dict. These are values, and here we have the key. This is going to be np and the array. Keys, values. That's just this, and then we have to actually return the value from it. Often when I program in Python, I forget to do that because I'm used to F# and Spiral, and those are expression-based languages. But whatever is at the end of the chain of statements gets returned as an expression. So this return in F# would be implicit. Okay, so we have that. Wait, why is this key? Oh wait, this is wrong. Yeah, I guess I have to do the Hopfield thing. Maybe I need to get and then wait, expected values. So this is a key. Yeah, so it gets yeah, this is fine. Of course, now we don't need these updated current policy. We don't need the moving average updates. That's going to be implicit in the as a result of the softmax. Implicit as a consequence of the softmax. That's what I meant to say. Not a result, but a consequence. And is there even a difference between a consequence and a result? I guess a consequence is unintentional in general parlance. I think they can be considered the same thing. Okay, so we have to do the updates at the end of all of this. And how we'll do is, I don't know, I guess we have to simply add a row to the matrix. Okay, how do we stack in Numpy? I think Numpy has np stack. Maybe we can use this. Let's see it. np stack. It has row stack and column stack. So which one exactly do we have to use? Okay, let's experiment a little here. Instead of printing this, let's try stacking the input. Np stack keys input print. So it takes a sequence. Okay, so like this. Okay, let's see what this does. Maybe okay. Let's try stack row stack npv stack. Okay, vertical stack. Oh great! This ended up stacking this to the bottom of the array. Yeah, nice. Okay, this is what we need. npv stack. So let's see. npv stack current policy. Is then key. And also we have to do npv stack current policy values, and then this updated current policy. And it kind of occurs to me that I probably should find some way of abstracting this. It's pretty unbearable to have to keep doing this, passing the keys and the values separately. I mean, how would we attempt to do that? I mean, yeah, but then I have to go in and kind of create separate helper functions for the keys and the values everywhere. No keys, no values. Oh crap, I fucked this up. Yeah, this is one of the flaws. When you copy paste widely, you cannot end up making errors. So it's not really a good thing to have them be separate like this. But never mind. Let's just keep going like this. This isn't really the best programming practice, but this is just a sketch, and I don't feel like um, average pulls this key, and then values, and then we just add the average policy update. Wait, is this really right? Like, here we have the updated the current policy. Oh, yeah, this isn't right. We have to put in the current policy update. That will get averaged out. If you cannot get the abstraction right, at least get the naming right, and that really saved me here. Because when you're editing the program, you cannot really think about 100 different things at the same time. So having the correct naming really helps focus you. Updated current policy. Okay, let's do this like so. Okay, so this is this. So we updated the current policy, the average policy. Now we just need to update the expected values. Okay, so let's yes, let's not make a mistake. And let's change this to values. Oh damn. Okay, why did I? Now it's right. I think we could try running this, and we'll see what we get. Expected values, nominator, and the denominator, policy, keys, values. Okay, so what exactly do we print? Yeah, so we need it just for the first key. Okay. So let's do Hopfield dictionary. The input will be np in the array 100, and the keys will be the expected values. Normal keys. Oh yeah. Actually need expected values. No, actually, let's skip this. Yeah, this is complicated. Let's make this the input equals this thing. Oh, let's replace it. Let's replace these two. Oops. Okay, so put in closing parentheses by accident. Okay, but then now I have it. Now we can try running this and let's see what comes out. Input operator minus has a mismatch in its core dimension. Okay, where is that happening? Print Hopfield dict. Okay, whatever. Let's just print this out and we'll see what's the problem. Input is so input seems to be empty for some reason. Yeah, NDRA, that's a fucking type. I was wondering why it was green. Sorry about that. Let's just remove the print statements. Expected no please, expected no values. Okay, this is as is expected. Okay, this is wrong. This should be 150. This should be 187.5. Okay, so let's dive into it and we'll see what's the problem. New expected values. Have this. Okay, let's just print out the arrays directly. The end. Let's see. This. Wait, I think I get it. I understand what mistake I made. Like this doesn't actually mutate the current policy keys array. Okay, that was a foolish mistake. Okay, let's do this. Like, okay, let's put this into global. Um, I can never figure out how Python's scoping rules work. Like previously, we had no trouble fetching the globals, but now it's complaining about them. Whatever. Okay, let's try it. Let's try it again. So yeah, now it's adding. Yeah, and you can see these are the values. 150, 127. And once these two get averaged out, we should probably get the correct value. Let's see. 0, 0, 0, 0, 0, 0. This is, yeah, 75, and this is 0.5. Should be, there should be 150, and this is now 125, and this is 125. What the fuck? Yeah, because I forgot to put in the denominator here. Let's print this. Yeah, this is now. Let's print these two. Yeah, now it's right. Let's rerun it again from start for good measure. Yeah, this is exactly what we saw in the tabular implementation. So the expected values here are getting updated properly. And I guess the only thing we can also check out whether the let's put in 0 here. Yeah, now we have the weights correct. This is 75 and 50, and once they are divided by 1/3, this is going to be 150, and this is going to be 225, which means that the expected value calculations over here will be correct. The don't thing that I'm wondering is whether the policy updates are correct. So let's print that out. Let's first commit this. The expected new updates are correct. I haven't committed in a while. So we need the current policy keys and the current policy values. Policy values. And we also need the average policy keys and the values. Average. Yeah, so this is what it is at the start. This is the average policy. After the update, it ends up being this. So yeah, okay, the average policy update does make sense because this is roughly in the same ratio. Is it? Yeah, I think it is. Maybe this should be a bit big. Maybe this should be a bit bigger, like 0.375 something. You know. No. 12. 125 times 3. Yeah, it should be like 375. Yeah, so yeah, this most likely right. Now is this. And this roughly seems right. Okay, what we'll do is compare it to the other example, to the tabular example. Let's see, the current policy and the average policy. Let's figure that out. Let's give it a try. Okay, so this how it is at the start. Wait, also, yeah, I need to set this to 0. Otherwise, the example won't match. So 300, yeah, this is how it should be at the start. 75, 225, minus 80. So yeah, it's kind of, it's only slightly off. Let's see, What's this terminal? Let me close it. So yeah, 75, 225, 0.125, 0.375, 375, 87 minus 165. Okay, what I'm going to do, okay, let's just copy paste this in a file so we can compare it more easily. And I'm also going to rerun this again. And I think we could split the panel. And now we can more easily compare this. Like, we have, no, I cannot have both at the same time. Oh, actually, I can have, surprisingly. Oh, wait, these are the same tab. What the fuck? Okay, now they aren't the same tab. Okay, and is this? Let's think about this more critically. The stuff the one on the left is the tabular implementation. And this thing here, and this thing here, these are the unnormalized policies. So you can see it's roughly, the ratio is roughly 3 to 1 here. And that should be added to this distribution here. And this is 1 to 3. So yeah, they should be roughly even after the update. They're here. But I think, yeah, I think this is wrong. And I'm not exactly sure why. The minor differences in the values between the two versions are because the softmax has a temperature, so it ends up assigning some probability to the other inputs in the array. Oh, let's see, what exactly is the temperature here? 0.01. I mean, if we increase that even further to something like 0.0001, I think now there shouldn't be any differences due to numerical values. Really, 75. Divide 25, really? I mean, okay, so they're exactly the same. And yeah, so there's something wrong with the Hopfield dictionary implementation. It isn't correct. I think the average policy here is correct, and I'm not sure why it's not correct here. We're going to have to figure that out. So let's print out the. We also need to figure out why there are these minor differences here. 75, 225, minus 80. Okay, let's start at one thing at a time from the smallest issue. Let's investigate and see if we can figure out why this is 75.25 instead of exactly 75. That's the best thing to do here. Is my camera off, maybe? Okay, let me put it like this. Like, there shouldn't be minor inaccuracies. So the new expected values, oops, let's bring this, why is this happening? This is very weird. Sometimes I switch keyboards due to some weird key combination. I don't know what key combination it is. I'm going to have to do some research in order to figure out why that is happening. In fact, let me ask Perplexity right now. Would I switch keyboards? I mean, not the keyboards, the keyboard layouts. I wonder if there's some other shortcut apart from the Windows and the Space tab. Alt Shift. Really? Alt Shift. No, I mean, I'm pressing Alt Shift here and it's not working. Oh yeah. Because I haven't tagged to hotkey. So what I have to do is press. I mean, because I haven't tagged two different keys when I'm pressing them for a short period of time. So when I hold them for a bit longer, when I hold Alt and Shift for a bit longer, it switches the keyboard. You can see it in the bottom right corner. Okay, how the hell do I disable this thing? It's constantly switching it by accident. Can I disable? When I typing between input languages change mini sequence. Switch input language, switch keyboard layout. Okay, let's diamond language. I guess it's typing. Let's see. Typing advanced keyboard settings. Let's see. Advanced keyboard settings. Input language hotkeys. Is that it? I think that should be it. Between left alt and shift. Change key sequence. Control shift. Wait, it for a minute there it went completely away. Weird how different this is. Okay, never mind. Okay, let me click on apply. Yeah, so now I'm not going to be annoyed by this every time. Yeah, these chatbots are amazing. I mean, at least for trivial things like these. They really save me time looking things up. I kept changing the keyboard layout constantly by accident. Then I had to press Windows and the space key to do it explicitly. I'm glad that I figured out what the problem was. Okay, so we have the new expected values and average policy update and the updated current policy. And we have the current policy update. Let's comment this in current policy update. We'll print I can also leave this out. New expected values, current policy update. Okay, so this, I guess this makes sense. And then let's print out the updated current policy. Uh, 75, 225, minus 80. Yeah, this is what we want to see in this CFR sketch. So new expected values, current policy update, and okay, we cannot print out the updated current policy, except maybe at the end here. Wait, what? Wait, no. Got to comment this out. Expected values. This is 1, this is 30, this is 0. Wait, 1, 3, this is 1, 300, and 0. Why is this 1? It shouldn't be 1. That's very weird. I mean, that's probably the reason why we're getting weird results. Yeah, this should be 0, this should be 300, this should be 0. But when we run it here, we get 1, 300, 0. Where's this 1 coming from? Values, then nominator. I mean, could it come from here? I don't think so. Okay, let me print out the expected values that we're getting in here. In calculate expected values, the expected values is 1, 0, 0. Excuse me, just a moment. I need to check why my mobile is ringing. I guess some spam must have triggered it. Never mind. So let's see, new expected values, like, it's already a problem by the time it gets here. Sample probability, okay, let's see, E, and this is expected values key. Okay, let's print out the E. Print E. Okay, so it's a problem here. Yeah, probably the passing keys and values. Keys and values. F, B, B. What? What the fuck? Oh, no, it's suddenly correct. As you can see, when I print it out, it has this one here, but when I don't print it out, when I also print out A and B, mm, is this some kind of weird memory corruption bug? Okay, this is a very weird error. I have no idea what to think about it exactly. Let me just print out. Before we even do any updates, let me print it. Let me print this out. Yeah, so it's all zero. It's okay. Let me pause here. I need to think about this more deeply. Okay, viewers, I managed to figure it out, and I even opened this issue on the Numpy repo. I managed to pare it down to this minimal example. And you can see when I try running it in the terminal, I cannot get the weird results from run to run. Well, let me prove it to you. Okay, this is as is expected. But when I leave these two out, you can see how these how the elements of this array are completely random. So yeah, I can only assume that there is something wrong with np.divide. Okay, let's do np np maximum. I'm going to set it to 2 minus 30, something like this. Let's see. Yeah, this works. Oh yeah, it's very weird, but I guess it's sometimes you run into very weird bugs, and perplexity really tricked me here. And it's when it comes to division by zero, it's always kind of nasty. Like if I was doing this in a GPU kernel, I'd just put in some kind of an if statement. But since this is NumPy, I'm not really sure what the right thing to do is. But this is fine. So let's see. Let's actually fix both of these examples so they aren't using this np.divide. np.d. So it's like this. Let's also deal with this. I just want to say that this is not at all my own fault. There's no way I could have possibly anticipated this. So let's see, where exactly are we right now? Okay, this is tabular, this is the sketch. Whatever, let's run it again. And calculate. Okay, so the E is now 000. Yeah, this now seems correct. Let's see if we. Let's go comment some of these out. Okay, so now this is 75, 25, 02, 012, 0.375. Expected values, expected values. Yeah, let me think. What exactly is going on? Yeah, here are the current policy keys, average policy keys. Okay, so uh, 8.3. Oh yeah, this is from the tabular representation. 237.5. Okay, we need to try all of this again. I lost track of what is what exactly here. Current policy, average policy. Oh, let's run this all again. Okay, sorry, I didn't copy paste it far enough. Okay, this seems okay. No. Oh, let's yeah, let's see what's going on here. Okay, we can see that pretty much everything is the same here, and that's up to this point. This thing in the tabular implementation is different from the Hopfield dictionary implementation, and I don't really understand why that is exactly. Okay, now that we figured out one issue, now we can work on the other. Figured out the Numpy issue. It was related to the np.divide. Also, in this bug, well, let's just put in a link to it. I don't really want to link to the Numpy issue, the git commit, so I just put in a comment here. We can kind of get rid of this bug report. We don't really need it anymore. Okay, so we have this, and yeah, now we have to think about what the tabular update is doing exactly. Current policy update, updated current policy. So we need the average policy update. Okay, let's bring that out. The average policy update 0.7326. The average policy update 0.25.75. Okay, that makes sense. You know, when you average these two out, you can get 0.33 on both sides. So why are we getting that on? Just copy paste this. The average policy update. Let's see, the average policy update. Let me just disable some of these print statements. Just what the hell is going on? Level 3. Oops. The average policy update, that's the same as in the tabular. And the average policy update here is, well, what the hell? Yeah, it's this thing is this thing should be like 0.73 and 0.27, something like that. So that's the problems. But why exactly do we have that problem? Like, what's this C? Oh, I'm adding C. No, yeah, that's actually right. No, that's not the problem. But maybe it wouldn't be bad to actually print out the C. No way. Let me pause for a bit so I can think about it. I understand what is going on, and this particular issue is unbelievably subtle. If I went straight into a GPU implementation, there's absolutely no way I would have realized that this algorithm has this kind of problem. It's possible to fix it, but first let me describe what's going on. Suppose I run this, you'll see exactly how it goes from the start. The current policy is this. This is the update. And after the update, the policy ends up being this. And this is the average policy update that gets added to the average policy. Over here, this C is this is the current policy, and this is what it is after the update. This is the current policy update. And as you can see, the values are much larger than with the previous policy. And after the update, check this out. You'll see that it's not the same thing as adding this number to this. Instead, it's that number added to that, and then it's I won't say it's divided by 3. It's like it's basically a moving average update. So that's why the updated current policy ends up being much smaller than one would expect. And the average policy update ends up being this. And this is not the case with the CFR Sketch HD. Here you have the C, and this part is pretty much the same as in the previous algorithm, in the tabular algorithm, and this is completely different. And the updated current policy here is what you would expect to get by adding these two numbers together, and that's not actually the correct thing to do, unfortunately. And this caught me completely by surprise. That's why the average policy update is so large. And it can be hard to understand why this is the case at first. But the natural is that we have to update the average policy update based on the current policy. And the current policy we don't get by adding the previous policy and the current policy update. Instead, suppose we, for example, stack the current policy keys and values and then took the softmax of it, we'd get something completely we'd get what would be equivalent in the tabular example. But that's not the same as adding the current policy to its update. And it's possible to fix this, and it's just that we're going to have to also do the same trick as we did in expected values. Like we're going to have to put in okay, this is basically the numerator, and we're also going to have the denominator. And in fact, right, if I really think about it, we don't need the keys for every single one of these. I have no idea why I did this. Yeah. Okay, let's improve the algorithm a little. Keys. Yeah, I mean, we only really need one of these keys. Average policy keys. Wait, what exactly did I do here? Let's rename these to keys. Now this is much easier. Keys. I'll just fix everything one by one. Like, whatever, we don't even need the keys field here. Yes. Wait, why do we still have this? Yeah. Okay, so this is the keys. And the Open Dictionary. Whatever, we don't even. Okay, we do have to pass the keys. Okay, so now we only have a single keys array. In the current policy, we're going to rename this to numerator, and we're also going to put in, let's say, a denominator. So how are we going to do that? I'll just put let's just fill them with ones. I mean, it doesn't even have to be like this. We can just yeah, have it be like this. We only really need one. We don't need a separate denominator for every value. And yeah, we can just rename this to average policy, current policy. This is the expected values nominator. Okay, like this. Okay, so current policy, what we have to do is, yeah, basically this. This is the current policy update, and this is going to be the denominator. Current policy. Let's see. We're also going to store at current policy denominator. Oops. Current policy update denominator. We cannot make. Yeah, we must be careful not to make shadowing error by accident. Okay, not bad. Now that we have this numerator, we also need the C denominator. That's current policy denominator. So what will we do here? What will we do with this? Okay, we're never accessing this, but now we have this C numerator, current policy update. Okay, how about this? C denominator, current policy update. Wait. Sorry, this is just a print statement. I shouldn't be doing this here. Let's see. Okay, so that's why this happened. It's true. In the perplexity example, it did use an out. Sorry, I got interrupted, so I kind of lost the thread of my thoughts. So yeah, I wanted to comment this out. Now in the average policy update, we have the C numerator. And we have the current policy update. And this is going to be the numerator. Okay, so what exactly was I planning to do here? Was I supposed to maybe divide this by the denominator? What exactly? Like, okay. So instead of saying C num, I just use C everywhere. Now let me rename this back to C. I'm going to make this C num. And this is C, C equals C num divided by C denominator. So yeah, now we have the C. This is the current policy. Is this what I was going for? I'm not really sure. Okay, let me pause here. I need to think about this more. I don't think I really thought this part through exactly. Sorry about this. Okay, I figured it out. Sorry, I think I having the denominator be like this. No, it really isn't what I intended. Instead, what I meant to just is what I meant to do is just put in a one here, and that will keep track of the counts in the softmax. It doesn't. Yeah, it doesn't even have to be in like current policy denominator. Instead, we can just have it be a count. Let's put it as a count. 111, and okay, this is just going to be current policy. I'm going to stack it. And yeah, we don't have the. We're going to just get the count here. This is going to be C. This is going to be the count. And yeah, this is fine. Now that we have the count, what we can do is basically undo it. Count 0. Basically, we're going to undo the averaging effect, and I mean, in fact, we can actually get the same thing by simply multiplying this by the count, and then that would be more numerically stable. So let's do it like this. Okay, now let's see whether this. Whoops! What did I do? Which policy update? Input brand 1 has mismatch in its core dimension. Okay, maybe yeah. Let's put in the type equals float. No, that wasn't it. Yeah. We need the count. We need the count. Let's try this again. No, that wasn't it. Whoops. Yeah, I am shadowing it here. Okay, so instead of that, let's see. Yeah, God damn it. Current count. Okay. Based on this, I can already tell that my fix didn't work, but I think we're going in the right direction. Okay, let's print out the counts. Print f current count 0. Okay, so it's one here. Uh, oh crap. Oh yeah. I mean, of course, it's going to be one. What the hell was I thinking? Okay, so this is a failed attempt at fixing it. I'm going to have to think about this again. I thought the count would be something like 0.5 here. Uh, um, I need to go back to the drawing board. Okay, I've had time to think about it again, and after thinking about it thoroughly, I don't actually think it's possible to really fix this. Not in the way I want. One way of doing it, I mean, I can think of two ways to fix it, but both are one is good, one is bad. Let's go with the bad first. Let's rename this to current policy. We don't need the denominator. This is the current policy update. And let's see this. So for the average policy update, we cannot use this, unfortunately. Current policy denominator, we don't have that anymore. Okay, let's put the average policy update. And it's not going to be like this. It won't rely on the current policy update. Rather, after it's added to the softmax array, we're just going to run it again. Let's see, we have to get the current policy again. We have to get the probability distribution from it. Current policy probs. Yeah. Then we can test out the average policy update. I mean, I can't really see any other way but to put it in the array and then do the whole softmax thing again. That way, the averaging will be done in a correct manner. So let's give it a try. This is this. Average policy update. This is this. Yeah, now I think it's correct. And this is what we were aiming for. Let's run this. Yeah, it's let's just copy paste this. We'll put it here. Yeah. Okay. So that makes sense now. I mean, that's one way of fixing this issue, and I'm actually very glad now that I'm doing this prototyping, because some of these issues are very subtle, and it would have been very hard to actually catch them uh, during the work on the GPU version. It's really helping me understand the algorithm better. So yeah, this is one way. And the disadvantage of it is that we have to get the current policy probabilities all over again, and that involves doing two matrix multiplies and a softmax over the entire array. So I'm not exactly thrilled to be doing this. I just don't really see any other choice but to do this. And the other is, let's see. The other would be to do what? To actually do this update at the very start. So for that to work, we actually have to change both algorithms. And in fact, this way of doing it is how actually how the CFR algorithm works in the papers. So kind of by doing this at the end, that's kind of my own special tweak. And I see now that there are definitely advantages to doing it how it was done originally. So let's do the average policy update, and it's going to be done right at the start. Whoops. Average policy update. We're just going to do them of the current policy probabilities. Yeah, this is going to be done like this. And also in here, it's not going to be done. It's not going to be done based on the updated current policy. It's just going to be done based on current policy probabilities. And actually, yeah, I don't think I need average policy update. I mean, this is already a probability distribution, so I don't need to do it twice. Okay, so let's do it like this. Update and current policy update. So let's see if we get the same results and when we try running this. I mean, it's kind of lame how this. Okay, so the final result is 0.25, 0.41, 6. Yeah, so it's kind of updating it in a backwards manner. It's kind of lagging the actual current policy. Yeah, but at least the algorithm would work. And we're going to be running this for a million times, so it's going to converge anyway. It doesn't really matter if the iteration is off by one. Yeah, it's very shocking that we couldn't do the update in the Hopfield dictionary version based on the current policy value. But I guess that's how things work. Well, so yeah, let me pause here. Let's end today's session here. I'm really happy how it went. Mm, I've been urging myself to work harder and to try to get into it, but now that I have actually began, I have in fact began to get into it. So it's very good. And what we've proven today is that the pretty much the entire CFR algorithm can be implemented using Hopfield dictionaries. So there's nothing preventing us from going further and eventually making a GPU implementation. The main difference is that between dictionaries and Hopfield dictionaries is the dictionaries have a login access time, while Hopfield dictionaries have at the very least a linear access time. In other words, ON complexity. And they involve doing these matrix multiplies and okay, so on something like Leduc, we can probably get away with a fixed array of 10,000 elements, and we'll just use it like a ring buffer. So when it gets filled up, the older items will simply be ejected. We won't be like just stacking elements infinitely, like we have in this sketch here. But when it comes to no limit hold'em, even I'm not really sure whether we're going to run with some unforeseen difficulties with how Hopfield dictionaries do abstraction. I think that the way it does should help the algorithm, but it's not really a certain thing. I won't really know until we try it out. Also, I'm not sure whether but really the minimal size of these matrices in terms of number of elements. I mean, in terms of number of keys, is enough. Will a million keys be enough, or will maybe 10 million or 100 million be the minimal requirement for the algorithm to actually work well? I simply don't know. So even though we're moving forward, we're still taking a risk. It's not such a huge risk as it was before with the backpropagation-based methods and the evolutionary methods, because over here we're still doing tabular reinforcement learning. It's pretty much the same algorithm. We just took it and put it on a different substrate. Instead of using regular dictionaries, we're going to be using these probabilistic dictionaries that I am calling Hopfield dictionaries. So we're not going to be plunging straight into the implementation on the GPU. We have to follow all the steps. First, I want to go over from the top and reimplement all the CFR algorithms on the host and we're going to integrate them with the Leduc game. So first is the enumerative CFR algorithm, then reimplement the Monte Carlo variance reduction CFR algorithm. It's called VRMC CFR. Let me rewrite it. This is also in native Python. I mean, not in native Python, but it's in Spiral. Then implement the VRMCCPR algorithm with Hopfield dictionaries. And why is this important? Because we're going to, once the algorithm has converged, or in other words, after it has run for a fixed number of iterations, we're going to spit out the average policy probabilities. And we're going to compare that between the enumerative and the Monte Carlo versions, both which use regular dictionaries and which use Hopfield dictionaries. And then we'll be able to know whether the algorithms are implemented correctly and whether they even work. And all of the above is easy. Now, what's going to be hard is implement the VRMCCPR algorithm with Hopfield dictionaries entirely on the GPU. Okay, this is going to be hard, and I'm going to have to learn how to finally. I'm going to have to finally use. I'm going to have to learn how to use the Catalyst library. And I'm going to use the Catalyst library and its queued backend to actually implement the Hopfield dictionaries. And that means implementing the fused matmul softmax matmul kernel. And in 2 videos ago, I went into great detail why this will be necessary for efficiency. It's going to the intermediate steps. This intermediate step, unless I somehow use it away with the third step, is going to produce simply two very enormous intermediate matrices that won't possibly that they're going to be impossible to store in global memory. They're simply going to be too large. So we need this fused kernel, and of course, besides that, we need to figure out how to use the algorithm along with the game entirely on the GPU. So we have our work set out for us. Everything above this is easy. All of the below is hard. So the next few videos is just going to be me going through this, and then we're going to have to go through a trip through hell. And hopefully after all of this, and hopefully after all of this, we can start poker botting. This is going to make us a shitload of money. Right now I'm kind of, coming from the Tau City job, I made a lot of money. Like, I have 6 figures now. It's probably going to go under 6 figures once I close the company, unless I manage to get this job that's line up to manifest. But even that is pretty much enormous amount of money for somebody in Croatia, especially for something like 10.5 for like 10 months of work. It's pretty much like a couple of yearly salaries for somebody here in Croatia, and I pretty much saved it all up. It's kind of one thing to say that it's like a yearly salary, that it's like 10 yearly salaries in Croatia, but most people who make those yearly salaries in Croatia would actually end up spending it because they have month-to-month expenses. I pretty much have nothing. So I'm very tempted to just sign up for trader training with SMB capital, or research and backtest trading strategies. And I'm taking a lot of opportunity cost by taking this approach with poker, and I do hope that it's going to work. But after I worked so hard at the Tower City job, I do deserve a year-long vacation, don't I? Yeah, I think I do. And this is basically going to be my vacation. I'll be doing something that I want and something that could enrich me by a lot. And this is essentially, maybe it's not the pursuit of singularity anymore, but I'm still using and practicing my skills at machine rationality. What we're doing here with the CFR algorithm is pretty much working on our own very small domain-specific probabilistic programming language. It has all the elements, and once we actually begin working on subgame solving, and that's going to be an even deeper plunge into probabilistic programming. I figured out how to actually do subgame solving efficiently. It's going to take dragging along the private, the private range of ends. I mean, their probability distributions along the trace instead of having to do restarts. But yeah, we're going to talk about that later if it comes to it. Yeah. Yeah. Besides this, yeah, we need to figure out. We need to deal with subgame solving. This is going to be hard also. I'm not kidding. So yeah, this part requires a lot of lower programming. Using the algorithm along with the game entirely in the GPU, that's stage functional programming. This is probabilistic programming, and all these steps require really high attainments in all of that. Maybe I can kind of, great. Yeah, it's possible to inline the text. I'm very impressed with how good Xcalc Draw is. So see you in the next video, and stay safe. Keep it steady. Don't lose your cool like me and get fired. And I'll see you in the next video. Bye bye.